All right, Evelyn, shall we get started?
Sure. Well, I'm happy to get started. So welcome everybody. Welcome to the 21st MIT InnoTherm. We're thrilled to have you here and really have an exciting colloquium planned for you today. Go to the next slide. So the focus of this colloquium will be on advances in additive manufacturing for heat transfer applications. We have excellent panelists that Sonia will introduce. And Professor Shania LeBlanc will serve as the moderator for this session. She is Associate Professor of Mechanical and Aerospace Engineering and the Director of the Energy Innovation Research Initiative at George Washington University. She's had multiple experiences in her past, including serving as a research scientist at Alphabet Energy and received her PhD in Mechanical Engineering and Materials Science at Stanford University. She's a recipient of the NSF Career Award in 2020, as well as ASCE 20 Under 40 High Achieving Researchers and Educators Award. And her expertise is very much aligned with the topic of today, focused on energy materials and systems, scalable and advanced manufacturing, and thermal transport. So please join me in welcoming Professor LeBlanc.
Thank you, Evelyn. I'm so excited to be here. This topic is what I spend so much of my days and sometimes nights thinking about, and I'm very excited about this panel. So let me get you introduced to the panelists. You'll see that the lineup of the panel is perfect for this topic of additive manufacturing for heat transfer applications. We've got experts in all aspects of that. So I'm going to jump right in and start introducing you to our panelists. Our first panelist is Bill King. He's a professor at the University of Illinois, Urbana-Champaign in mechanical engineering with courtesy appointments in material science and engineering and electrical and computer engineering. And I think this is really interesting. It shows his ability to really bridge out of academia and understand where applications are going. He's co-founder and chief scientist at Fast Radius. He has been founder of the Digital Manufacturing and Design Innovation Institute, which is one of the first manufacturing innovation institutes in the US. He's co-founder of Anisys Instruments, which was acquired by Bruker, and is on the Defense Sciences Research Council. I'm really excited in the way that Bill is going to contribute to this topic. You can see his research areas in nanomanufacturing, materials processing, digital manufacturing, and heat transfer. What I think is so wonderful about Bill's work is that he brings together materials, manufacturing, and design in a way that they're all intimately connected. He doesn't do it sequentially. And so I'm really excited to see how he's going to talk about those topics today. Our next panelist after that, one moment, let me advance the slide for you. Our next panelist is Professor Jae-Sung Song, who's an associate professor at Ulsan National Institute of Science and Technology in the Department of Materials Science and Engineering, and he's in the Center for Future Semiconductor Technology. Professor Song has received many awards, the Rising Star Distinguished Professor at Ulsan, the Best Award at the 3rd International Conference and Exhibition for Nanotechnology, and Presentation Award for the Conference for the Korean Institute of Electrical and Electronic Material Engineering, as well as being a member of the International Thermoelectric Society. His areas are thermoelectric materials and devices, nanoparticle colloid chemistry, and 3D printing, and solution process thin films. He's going to bring some really innovative ideas and examples of how he has integrated material science with manufacturing for thermoelectric technology. So understanding this materials to systems bridge that I think we all need to work on when we're thinking about how to integrate additive manufacturing for heat transfer applications. I'm very excited to see him talk about his work. And then we'll have Professor Ole Sigmund, who's a professor at the Technical University of Denmark in mechanical engineering. And he's a member of the executive board of DTU. He's president of the International Society of Structural and Multidisciplinary Optimization, president of the Danish Center for Applied Mathematics and Mechanics, a member of the Royal Academy of Sciences and Letters, and a member of the Danish Academy of Technical Sciences. And his areas are in theoretical extensions and applications of topology optimization, advanced and architected materials, and multi-physics optimization. And I think what's so innovative about his work and so broad and far-reaching is that he is able to show how topological optimization actually can touch so many different applications and so many disciplines. And in this particular panel, he'll be focusing on how it touches on heat transfer applications. So this is a great panel lineup. Before we get into what you're here for, which is hearing from the panelists, I want to cover some of the logistics. So each of the panelists is going to give about a 15-minute presentation of their research and some of their broader ideas in this area of additive manufacturing for heat transfer applications. And then we're going to have about 30 minutes for discussion. I'm going to ask that for that discussion period, you submit your questions or comments that you'd like to provide using the Q&A button in Zoom. And so we're going to be pulling questions from that stream that's entered into the Q&A. And please also submit any suggestions you have for future topics or speakers, and I'll remind you to do that at the end when I let you know what the next colloquium is going to be. As a reminder, this colloquium is being recorded and will be posted on YouTube. And this may include the questions, which we can't get to today. And if you prefer that your question be anonymous, please state so in your question. All right, so just to make sure that we've got the audience engaged and draw you into this topic, we are going to start with a poll. So I'm going to launch this poll. And in this, we're asking, in how many years will additively manufactured heat exchangers and thermal management devices penetrate and have high impact in an application? So we're asking, I know we're asking you this before you even hear from the panelists, but we'd like to see where your thinking is right now before you hear from them. All right, we've got almost everyone voting. It looks like everyone might vote. So I'm going to give a couple more seconds. Okay, it looks like we've stabilized. So I am going to end the polling, and I will show you that we're almost tied between 1 to 5 years and 5 to 10 years, with a few folks thinking that it'll take more than 10 years. So that's a great way to launch into our panel discussion. And then we're going to try to hear from you after you hear from the panelists and see if maybe you have the same thoughts or if your thoughts have changed. So with that, I'm going to turn it over to Professor Bill King.
So good morning. Thank you so much, Sonia, for the great introductions. Thanks, Evelyn, for the invitation to be here. It's great to be here also with Ollie and Jae Sung. Today, I'm going to talk about heat transfer devices enabled by additive manufacturing. And so I want to start the talk with a question. My question is, what is the best shape for a heat transfer device? So let's start with some devices that we all recognize here on the left. They all have similar looking shapes. We see a lot of straight lines, right angles, tubes and fins that are straight and smooth. And we know why these devices look the way they do. These are geometries that are easy to manufacture. But what if they could be any shape at all? Well, then we would probably design things to look much more organic, like the human circulatory system, perhaps. We would choose an architecture that features hierarchical branching flows for efficient flow distributions. And we would have intertwined 3D geometries with non-constant channel cross sections, things that would enable high heat transfer rates. So some of these design elements are in fact accessible with additive manufacturing, and there are promising examples of what is possible here on the right side of the screen. These devices have fewer right angles, they have channels with changing cross sections, and so on. And so we see examples of what is possible, and we get excited about it. There are, in fact, many opportunities for additive heat exchangers. The new geometries that I mentioned, also economic benefits from elastic manufacturing that allows low volume and customized solutions. Overall, there's really a very large economic opportunity for additive heat exchangers. I've talked to senior leaders at almost every metal additive equipment maker in the world, and they all report that heat exchangers is the biggest economic opportunity for additive manufacturing, bigger than medical applications, bigger than structural applications, that heat transfer related applications is where the money is to be made, in their opinion. And so because of this industry is demanding new technologies and expertise. So there's a bunch of challenges too that we need to overcome. So there's relatively few examples of working devices and systems. There's a lack of software and design tools. In general, the engineering workforce and industry doesn't have the expertise to take advantage of this. And from the university side, we have few educational offerings that focus on additive for thermal fluid applications. Okay, so in today's talk, I'm going to describe 5 heat transfer devices that we've developed in my laboratory over the last several years, where we're trying to address some of the challenges. The first device I'd like to talk about is a cold plate mixer manifold. And so cold plate is a conventional electronics cooling device where we have liquid coolant that's directed over a heat spreader that's spreading the heat that's generated by electronics normally. And so what we have developed here is a device that has mixing structures that are integrated with the heat transfer device, so with the manifold. The way these mixing structures work, you can see in the lower left part of the screen, we have a developing thermal boundary layer. There is this twisted tape mixing structure that interrupts the flow. It sweeps the hot fluid away from the hot wall and replenishes it with cool fluid, enhancing the overall heat transfer. So we built and tested a bunch of these devices. The paper here that we report many details of simulations and design and testing, but just to give you the highlights, we were able to, for this particular flow and architecture, we're able to improve the heat transfer within the device by about 2 or 3 times because of the presence of the mixing structures. So twisted tape type mixing structures are actually used in some mixing applications today, but the way that the twisted tapes are made is that you'll fabricate the twisted tapes separately and then insert them into the channels. And so that's of course a problem for long channels, skinny channels, or channels that are not straight, where you couldn't insert something into, which is what we have in this example here. I want to point out something that helped to motivate this particular work was the availability of new additive polymers that have very high accuracy and resolution in printing. This particular material is called cyanide ester, which has only been commercially available for the last couple of years. It's available from a company called Carbon 3D. And it actually has the highest temperature stability of any additive polymer, over 200 degrees C. It's also extremely strong. And so you can see here that we fabricated the tape and the channel all as one monolithic part. So this was a single print to make this manifold part. So this material, because it's so strong, we started brainstorming what are some other things that you could do with an extremely strong and temperature stable polymer material. And that led us in the direction of the second project here, where we developed jet impingement cooling apparatus that leverages this an additively manufactured nozzle. So here we have 2 gallium nitride power electronic devices that are mounted here on a PCB board. We have a high pressure air that enters the manifold, and then the nozzles direct the air immediately upon the devices while they're working. So you can see in the upper right just infrared images of the GaN devices and the jet cooler. The jet is on or off. So obviously we're cooling something. In fact, we get convection coefficient up to about 15,000 watt per meter squared Kelvin, in line with expectations. So we're not breaking new ground here with jet impingement cooling, but what we have done is we've consolidated all the parts. So normally, if you were to have a solution like this, you would have a bunch of parts that were made with CNC machining, and then they would have to be assembled together into the nozzle and the manifold. And what we've done is we've designed everything again in a monolithic part that combines the fluid management and the nozzles, and then directs the flow directly to where you want the impingement to go. And so the design freedom unlocks new architectures and ways that you could configure nozzles and devices that wouldn't be possible with conventional solutions. Now that use CNC machined assemblies. Of course, the polymer is nearly as strong as a metal assembly would be, strong enough for the application, and it's also much lighter weight as well. So there's other benefits. Now, of course, the jet impingement, the expense and complexity of the nozzle is not the only barrier for jet impingement cooling, but they are serious barriers, and we demonstrate how to potentially overcome them here. So the next project I want to talk about is a thermal storage device that uses phase change materials. And so in this system, we have developed a thermal storage device that's intended to be added inside a radiator loop. And so what happens is we have a cooling fluid that passes through this device, and then if there's a temperature spike in the fluid, it can be buffered by absorbing some of the heat from the fluid flowing through the device. And so what we have is this highly finned device, and we pack phase change material around it. Okay, so if we just look at the very simple thermal model of how such a device might work, in fact, it is the thermal resistance of the phase change material within the phase change material that limits the cooling power and limits the overall energy that can be stored in the phase change material. And so by having this highly finned device, we can promote higher heat transfer rates, higher cooling power, and overall access more of the phase change material in the vicinity of the device. So you can see finite element simulations of 3 devices. The first device is a device without any fins, so that's our baseline. And then by adding the fins outside the device, we get significantly more phase change. And then we also explored adding fins inside the device to reduce the thermal resistance to convective cooling inside the device. It turned out that was really meaningful. So for the device that has both internal and external fins, we had 3 to 4 times improvement in energy capacity and about 2 times increase in the cooling power. So we actually got very excited about this potential to improve the internal flows, which inspired us for the next couple of projects that I'm going to talk about. So here we just said, well, what can we really do to improve internal convection? And so for this problem, we have defined the problem as constant surface heat flux on the outside of a metal channel. And then on the inside, we have fins, and we allowed the fins to be different shapes. And we developed a method where we couple a genetic algorithm with fast finite element simulations that allow us to search the state space. And I'm going to talk about the genetic algorithm in the next slide. But basically, we have developed this method for automating the design of the fins, and we said, can we come up with something that's better than just the straight fins? So if you look for like heat transfer augmentation inside, for internal flows, you see examples in applications where people will score the inside of the tube, or where they'll extrude tubes that have simple straight fins like the ones that I showed here in the middle of the slide. But what we've done is come up with a much more novel shape. And you see we get about 10x reduction in the thermal resistance for the device with this genetic algorithm fin we call the GAF. So we designed and tested these devices. Okay, so the final heat exchanger that I want to talk about today is a dual tube heat exchanger, where what we have done is designed a device that has both cold side and hot side liquid flows. They're flowing in opposite directions. It's a counterflow heat exchanger. And so we developed, we used this genetic algorithm. We improved it for this specific case, where we search for and find the optimal shape for this device. We're constrained by the hydraulic diameter, which we want to prevent the channels from getting too small. But you can see the evolution of the fin shapes across the design cycle, and some finite element simulations of flow within the channels. So we made these devices out of metal. It's aluminum, silicon, magnesium, a common metal from additive manufacturing. And you can see a photograph of the device. You can see CT scans. I'm going to show a video here. This is what the device looks like in the CT scan. So here we can see inside the device. I want to point out a couple interesting things. One is we staggered the fins on the outer flow section, so you can see the staggered fins here. You can see the inner fins as well. And we're actually very proud of the manifold that is totally integrated. So this is a monolithic part, no assembly. The entire thing was printed at one time. And we have the manifold that's been integrated. So we have the inlet and exit ports that we can attach to the fluid streams, and they are, and we have like a watertight separation between both streams. Okay, so we tested these devices. They performed very well. The heat transfer rates are, around 10 times higher for the fin devices compared to no fin devices. But when we started the project, we actually had identified a dual tube heat exchanger that's commonly used in some applications. So, and I have a picture of that here. So this is a device from a company called Sentry. This is a dual tube copper device. It's scored on the inside to augment the heat transfer. And it's used in water cooling and water chilling type applications. And so what we used that was a benchmark to say how much better could we do than a dual tube device that is commercially available. It turns out we could do a lot better. So our device is, has 40 times shorter flow length, 24 times lower mass, 26 times lower volume. We tested these devices at approximately the same heat transfer rates, but at these rates listed, the power density is about 23 times higher for our device, specific power 20 times higher. The pressure drop is 3 to 6 times improved as well. So we were really able to meaningfully improve the performance of a heat transfer application compared to what is done today using these 3D geometries. So before I close, I want to mention some of the challenges. There's really so many opportunities for researchers and engineers for additive heat exchangers. So this slide is just a list of really great opportunities for new technologies. So I just want to articulate what these are. So first, there's manufacturing challenges. So manufacturability constraints are different for different AM processes and materials. So, all of the specific manufacturability details are just different every time you go to a different material or a different machine. And those need to be figured out, what are the best ones for heat transfer applications. There's really a lack of structured and rigorous methods to assess manufacturability and to distill these into design rules. This is an additive-wide problem, not just a heat transfer problem. The qualification of complex shapes is also very challenging. On the material side, there's only a few high thermal conductivity materials, so we need more materials and better materials. The material properties are not well understood, they're not well reported. And there's all kinds of issues with material selection that need to get worked out, like water tightness, surface roughness, corrosion, and so on. And then finally, we need software tools. The fluid structure interaction is challenging, technically challenging. We need better software, and we need overall methods for designing devices, not just with the software, but also the engineering methodologies that would leverage software tools. So with that, I'd just like to conclude and say thank you very much, and I'll pass it to the next speaker.
Great, thank you, Bill. That was fascinating. So we do have questions starting to come in. I encourage people to go ahead and put your questions in, and we will pull the questions at the end. Next, we're going to move on to Professor Jae-Sun Song.
So let me start my presentation. Firstly, I appreciate this invitation for taking part in this excellent international colloquia on thermal innovation. Today, I'm going to talk about the recent advances in 3D printing of thermoelectric materials and devices. So let me start from the thermoelectric effect. The thermoelectric effect is a solid-state energy conversion between heat and electricity based on Seebeck effect and Peltier effect. In the Seebeck effect, by applying heat to the thermoelectric material, a charge carrier at the hot side diffuses into the cold side, which create the charge carrier density gradient and eventually output voltage. In Peltier effect, by applying electricity to thermoelectric material, we can create temperature difference across thermoelectric material, which can find an application of active cooling. Today, I'm going to focus on the thermoelectric power generation based on the Seebeck effect. One of the important benefits of the thermoelectric power generation is the very wide applicable temperature from the room temperature and up to 1000 degrees Celsius. Near room temperature, we can use our body heat for wearable thermoelectric power generation. We can also use industrial waste heat or automobile waste heat for power generation. Also, above the 700 degrees Celsius, we can use the radioisotope heat for the power generation. We can understand thermoelectric power generation from this figure. Please look over this left figure. This is the planar heat source. Once we contact this planar structured thermoelectric module on the heat source surface, thermal energy is transferred from the heat source to the thermoelectric material, and the other side, heat is dissipated. This heat transfer and heat dissipation lead to the creation of temperature gradient across the thermoelectric material, and then we can get power. And this power depends on the material property, the electrical conductivity and Seebeck coefficient of material, and delta T across the thermoelectric material. So we can say that this power can be determined by two important parameters. The first one is the material efficiency, so-called GT value. GT depends on three different parameters: electrical conductivity, Seebeck coefficient, and thermal conductivity. These three parameters are strongly correlated, so it's very difficult to increase GT value. So many people have focused on the development of the efficient thermoelectric material with high GT value so far. The other important part is the thermal design. This is the device engineering to getting higher delta T. For example, if we make a better thermal contact between heat source and our thermoelectric generator, or if we use some better, more efficient heat sink for better heat dissipation, we can make larger delta T to get higher power. Also, we can do thermal design for something like some geometrical engineering of the thermoelectric material for getting higher delta T. The device engineering is really difficult to be achieved by traditional manufacturing process. In this traditional manufacturing process, firstly, the ingot is synthesized, and then by two-step dicing process, we can get a cuboid-shaped thermoelectric leg. And then subsequently, these legs are assembled into the module. In this traditional process, we can find several critical issues. Firstly, we lose lots of material during the dicing process and synthesis. It's about 60%. Secondly, we always get cuboid shaped thermoelectric lag, and necessarily the device structure is always planar. But in a real world, the most heat sources are not planar, already have some freeform surfaces like curved structure, such as our body, a heat exchanger, and exhaust pipe already curved. And in our lab simulation, you can find a huge difference of the thermoelectric energy conversion efficiency in the case that the planar structure thermoelectric module mounted on the planar heat source and on pipe. Their conversion efficiency difference is more than 1 order of magnitude. So we need some new process for device engineering of thermoelectric devices. I think that 3D printing or additive manufacturing can be a solution for thermoelectric device engineering, because we can shape the thermoelectric materials and devices from the micro scale and up to meter scale. So from now on, I'm going to show you several examples of the 3D printing of thermoelectric material devices, including our lab recent reports. This is the first demonstration of the 3D printing of thermoelectric material based on the bismuth antimony telluride-based material, which is a workhorse thermoelectric material operatable at room temperature. In this paper, the authors used stereolithographic 3D printing process based on the ink of composite of photocurable resin and mixed with bismuth antimony telluride particle. After making some 3D shaped object, and then these objects were thermally annealed at very high temperature. Despite high temperature annealing, these final products still have some organic residue, which significantly degrade the thermoelectric property. So GT value was at the time just 0.1, which is just 10% of ingot property. Next approach is the selective laser sintering. In this process, the successive layers of the powder material, such as metallic materials or some ceramic material, are melted by high intensity laser in a selected area for consolidation them into a 3D structure. This process is quite beneficial for large scale fabrication of thermoelectric material. Also, we can preserve purity of the thermoelectric, inorganic thermoelectric material. So in some cases, you can find those various references in this process. And in some cases, the material property of GT value increased up to 1.2 in bismuth antimony telluride case. This is comparable to the material synthesized by traditional process. Also, in this process, the material is quite dense. So this material have quite strong mechanical strength. The issue in this process is very high, very expensive price of the equipment. And also this equipment is very difficult to be customized. So generally, people have used extrusion-based 3D printing process for the thermoelectrics. This process is a dispensing like a process, and ink was deposited layer by layer to make some 3D structure. In this process, we have to solve two material issues in inks. First issue is the colloidal particle issues, such as particle migration and sedimentation and confinement. Secondly, the rheological issue. The first issue can be solved by well dispersion of the particle into the medium. Second issue is more important, and typically the 3D printable ink should have some appropriate rheological property, such as the flow under pressure and maintaining their structural integrity after deposition. Such a rheological property is called thixotropy, which is easily achieved by organic binder addition. However, the organic binder has some critical limitations, such as low thermal stability and oxidation, and the most importantly, these are electrically insulating. So our group have designed some particle by introducing some negative Ni on the surface of particle, which generated a charged thermoelectric particle. This particle charging is beneficial for getting a good colloidal dispersion in an electrostatic manner. Also, this particle has a larger hydrodynamic volume fraction in the ink, so which can increase viscosity and elasticity in the ink simultaneously. So our ink have the higher viscosity and elasticity, which are desirable for the 3D printing process. So by using these inks, we 3D printed this curved structured thermoelectric material, which have the dimensions perfectly fitting to this ceramic pipe. After mounting these 3D printed thermoelectric N-type and P-type material on the ceramic pipe, we could fabricate some cylindrical thermoelectric generator. We measured the power performance by flowing hot water through this pipe, and you can see a reliable output power depending on the temperature difference. In this paper, I have collaborated with Professor William King. And for better resolution of 3D printing or for finer control of printed structure, we have to improve the rheological property of the ink further. So to this end, we control the particle size and size distribution more precisely. We have used a smaller particle with a narrow size distribution and getting higher viscosity. Also, we have precisely controlled the surface state by oxidation, and then we got quite very high viscoelasticity. By using these inks, we realized direct ink or 3D ink writing to produce a thermoelectric filament. Diameter of these filaments from the 100 micrometer to millimeter scale. And then we can design and fabricate some complicated architecture, P-type, N-type bridge structure, and some scaffold-like structure. And these thermoelectric layer have quite high GT values, about 1.1 for P-type and 0.5 for N-type. And then we have fabricated micro thermoelectric generator by direct 3D printing. And you can see this side of this module is about 2 millimeter, and you can see quite a reliable power performance depending on the delta T. And one should note that the delta T created across this thermoelectric lag is about more than 80 degrees Celsius, which is quite a rare case in the micro thermoelectric module because they are typically fabricated by MEMS technology. So high aspect thermoelectric lags are impossible in this process. And this is the last part of my presentation. Another important device engineering technology, sorry, for the maximization of efficiency is the segmentation of thermoelectric material, which consists of multiple dissimilar material with different operator temperature. The concept of segmented TEG is very similar to tandem solar cell. We can fully use the heat energy by this multi-junction of material. In this segmentation, we have to solve two different issues. That's the material compatibility, and also we have to optimize the lag geometry. So for the segmentation of thermoelectric material, we have realized a multi-material sequential 3D printing technology. By using this process, we sequentially deposit 3 different inks and then getting this multi-junction bulk material. And by adjusting the property of each layer, we realize very high average GT values in this material. And then we have measured their power performance. And you can see the height ratio of these 3 layers are having optimized by simulation and then fabricated this material. We have compared this material property with a single element, and you can see a higher power density of this segmented material compared with the single element material. Also, this segmented material exhibit quite high efficiency, energy conversion efficiency of the 8.7% under delta T of the 240 degrees Celsius, which was the record high efficiency so far. So let me summarize my talk. So far, I have shown some 3D printing of thermoelectric material devices. I have shown the various processes and diverse material and different structural modules, planar, tubular, micro, and segmented thermoelectric generator. And I also want to talk about some challenges of this for industrialization of this process. Firstly, I think that we have to increase the material efficiency, the GT value of the 3D printed thermoelectric material, because which is still lower than those of materials synthesized by traditional processes such as hot pressing and also melting method, just 50% of the peak record high value. And secondly, the full functionality of 3D printing have not been realized in thermoelectric materials and devices, such as some printing some complicated structures on large scale production. So we have to advance some 3D printing process. Thirdly, I think that some different material, different components in the device, such as the electrode and diffusion barrier material, which is very important in manufacturing thermoelectric devices, but have not been studied in 3D printing. Finally, the large-scale production. This is essential for the industrialization. Okay, thank you for listening. I will hand over to the next speaker, Ole Sigmund.
Great, thank you, Jae-Sung. Next, we'll move to Professor Ole Sigmund.
Yes, so thank you also very much for the invitation to give this talk and meet you people. And so we have seen some marvelous talks by Bill and Jae-Sung on what can be built, and also some design studies by Bill. And Bill was asking for systematic design methods. And that's exactly what I'm going to talk about. I'm going to talk about topology optimization, specifically with respect to heat transfer. So I don't know how many of you know topology optimization. Unfortunately, I don't have too much time to go into details, but I will just sort of devote one slide for that. If I can get my slides to shift here. That's interesting. Yes. And so if you haven't played with that before, I invite you to use our apps that you can download at the App Store or Google Play. Which demonstrate topology optimization at the tip of your finger for structural applications. The very basic idea is that you have a design domain and you discretize it by your favorite discretization method. That could be finite element method, finite difference, finite volume, or lattice Boltzmann, or whatever method. And you impose the boundary conditions. And then you assign a design variable to every point or every element in the design domain. And by gradient-based methods, you update the distribution of material between void or solid, or between two different materials, and you converge that using systematic gradient-based methods. And within a couple of hundred finite element or modeling operations, you reach an optimized design. And so this is very widespread in the mechanical engineering industry for solids. And we have been pushing those developments also to the extreme. For example, we were the first to optimize a full Boeing 777 wing structure. And we have lately also published a paper on optimizing suspension bridge decks with possible weight gains that demonstrate 30% saving potential with regards to CO2. So we have come very far in the topology optimization in structures. And essentially, you can apply this to all kinds of other areas. We have been working in, I will come back to the flow problems, architected materials, thermal problems, and also in optics and acoustics, we have done a lot. And so the essential idea is, well, if you can model your PDE with some discretized method, then we can probably also add optimization or topology optimization on top of it. So I've been doing this, or the community has been doing this for 2 or 3 decades. And in the early days, people would ask, well, you make all these beautiful structures, but what are they good for? You can't build them. But with the development of additive, well, essentially we can build everything. And you will now see, if you browse the internet for topology optimization or other names, that you can build all these marvelous structures and really take advantage of free material distribution and then optimize structural or other performances. The Dear Child has many names. Essentially, all these methods refer back to the same basic methodology where you design or you allow one design variable per element in the discretization, but the different methods may update the density distributions or the material distributions in different ways. So this was sort of the short introduction here, and essentially the field has moved into the fluids and thermal problems, and I will give you a series of applications that we have been looking into in my group and associates. And the first one directly directs to or refers to Jaesung's talk. A couple of years ago, I had a PhD project looking into optimal design of thermoelectric generators. And we looked at exactly the problem that Jaesung was showing before. And the question was, could we distribute two different materials and then get higher efficiencies? And for the standard setting, well, that actually turned out to be pretty hard. Essentially, it just wanted a simple segregation between two available materials. But what we did find out was that the design depends a lot on the application. So if you have higher convection coefficients or higher or lower temperatures, the distribution changes. But seldomly do we get designs that we see here where there's sort of a gradient behavior. Usually it just wants the discrete, either one material or the other material. So that was a little bit disappointing. One alternative sort of setup is where you put the electrodes in the other direction. So they are called so-called off-diagonal techs. And there we get slightly more interesting designs, where the lower one would be sort of analytical solutions based on simple laminates. Then the upper ones would be the topology optimized, and we could get efficiencies up to a factor of 2 higher. But these off-diagonal devices are still less efficient than the standard devices. So not much gain there. What becomes much more interesting is when you also add fluids to this. And this application was in collaboration with a Danish design company with the aim of designing natural convection or passive cooling of LED lamps. And the industrial designer in the project designed this beautiful structure here, and that was sort of our baseline design. Could we improve that by systematic topology optimization? And indeed, we could definitely improve it depending on how you place the cooling device. You would get different structures. And so this is for a device that was optimized for fixed position in one direction. And compared to the designer's best structure, you would see that some parts of the fin were not very efficient. Then with the optimal design, you would see that there's a much better natural convection and also no heated flow touches another part of the structure. If you introduce some symmetry, make it less dependent on directions, you will get different designs. And if you put it upside down, you would get yet again different designs. And so in collaboration with Renishaw, we also got these or some of these structures manufactured. So they were 3D printed in aluminum. For these early devices, we didn't take overhang into account. So there was quite a job in removing overhang. But then when the structure was cleaned, it fitted very well with the numerical expectations. And we could show that we were significantly better than the designer's best choice and a pin fin structure, and then this topology optimized structure. Now, Renishaw built these structures for us for free, but they told us at the point that these would cost more than $1,000 to print. So that's, of course, not very interesting. And so that's probably a general thing that maybe it's not always best to do 3D printed metal structures, but you could think of an alternative, and that is to 3D print your wax mold, and then you pour or you cast a metal into it, and then in that way you sort of do semi 3D printing of your devices, and this is much, much cheaper. Interestingly, here we had, when we did these manufacturing, we had some of our manufacturing guys also simulating the casting, and they told us this is a perfect device for casting. And that's of course natural because it was optimized for natural convection, and hence it's also quite kind of obvious that the casting, so the cooling process, would be quite optimal there. So there are absolutely no internal flaws there. We checked that with a CT scan also. So this was in natural convection. Another area we have been getting into, which is also quite complex and quite computationally expensive, is in topology optimization of heat exchangers. So fairly similar to what Bill was talking about earlier. And so we had a reference design where we would have cold water getting in and getting heated by a hot oil. And we tried to optimize the structure such that the pressure drop would be the same as before, but maximizing the heat exchange. And if we look at the design history, this is sort of a speed up of the design process. It gets extremely complex, and you would say also quite weird looking. It's 113% better. But you would ask, what is going on here? Is this some numerical artifacts? But actually, I think the optimization is trying to tell us something. It's sort of introducing what we all have in our intestines, or villis or microvillis. So these are small, you could call them dimples, that maximize the surface area and in that way improve the heat transfer. So interestingly, this is optimized for metal structure here, but if you lower the conductivity, so if you do it in polymer instead, then these dimples or villis would disappear because they're not efficient anymore. So you can learn a lot from studying topology optimization, and maybe you don't want to actually manufacture this complex device, but you could learn something from this. Now, everything I told you was for fairly low Reynolds numbers and steady state problems, but there are developments also going on in doing transient problems. Everything becomes more heavy. You have to do a forward analysis and a backward analysis for doing this, but still it's doable. I'm just showing two examples. This is based on a lattice-Boltzmann method where you have a membrane in the top that's just harmonically excited. And then by a careful design of this structure, you will get a pumping effect that pumps the fluid from the left to the right. The other device here, let me see, it disappeared. But this is a thermal energy storage where you have a rock bed where you introduce some heat and you distribute solid walls. And in that way, you maximize the heat efficiency when you have daily variations in storing the heat and having to extract it again. So it's definitely possible to do transient thermal problems also with topology optimization. And in the right side of the picture, we are showing a heat cooling device based on turbulent flow. This becomes, of course, computationally very heavy, and we also have some challenges because we have to identify the walls, to identify the boundary layers, and when we don't know the walls or the structure a priori, we have to introduce additional things in the topology optimization process to find or to identify the boundary layers and stuff like that. But that's, well, it's developing, but not yet available as commercial softwares. So this was a lot of talk about fancy structures, and essentially you can build them with 3D print. And interestingly, I've said for a while that AM and topology optimization constitute a perfect marriage. They grew up together. They both started in the 80s and they have matured and they have married now. Whether it was AM that proposed to TO or if it was TO that proposed to AM, I'm not sure. But definitely one thing is that in a perfect marriage, partners have to adapt to each other's flaws. And right now, well, additive has a lot of limitations or problems. It cannot handle overhangs, support requirements, residual stresses, and stuff like that. And we in the topology optimization community are trying to cater for that. So we take this into account when we do the optimization. But obviously, additive is also trying to improve on that and getting better and better processes. So just to show you two pictures of something we are trying to take into account, for example, overhang constraints. This would be two structures that are beam structures that are optimized with no restrictions, but we can identify some red boundaries here where you have an overhang that's not possible to manufacture. we can impose a constraint that hinders such overhangs, and well, we will get very different structures. And what we also note is that the stiffness is decreased by 20% when we introduce these manufacturing constraints. So there's no free lunch here. You introduce manufacturing constraints to be able to additively manufacture them, and you lose something on the performance. Just shortly in 3D here, we had a torsion rod. So you have a support and a torsion load here. When we don't have any constraints, we would get a structure that's difficult to manufacture because it has overhang indicated by the red. If we introduce an overhang constraint, well, then the structure becomes like a droplet shape that never has less than 45-degree overhangs. You get sort of funny structures. Also, if you want to avoid external support structure, you can also introduce that and you get structures like this. So this was structural, but we could as well introduce this on the thermal or the fluid problems. And so that essentially ends my talk. Some conclusions or outlooks here that we've come a long way in topology optimization, but we still have significant challenges. There are non-linearities, time dependencies. If you have problems in modeling your stuff, then definitely you will have problems in optimizing it also. We have seen a few examples in high Reynolds numbers, high-speed flows, turbulence, but this is still under development and certainly not available in commercial codes. And CPU times, well, some of these natural convection problems used 100,000 or at least 10,000 of CPU hours. We are trying to introduce reduced order methods for that. And we should note that accounting for additive limitations comes at decreased performance. And well, as I said, TO and AM must still work hard to maintain a successful marriage. We cannot retire yet. And well, with this, I've shown a lot of pictures. I'm showing various papers that you can look into. These are fairly ego-centered. But if you want to have a more comprehensive review, then Alexandersen and Andreasen have just published a very nice review on this stuff. And if you're interested in more like manufacturing constraints in topology optimization, Matthijs Langelaar has done a lot of interesting work there. So thank you very, very much for your attention.
Thank you. Those were fantastic talks. We have questions coming in. I think that it's going to be an exciting discussion for the Q&A. Before we get started on the Q&A, we do want to pose another question for the audience. And so I'm going to launch a poll for the audience members now to ask you which aspect of additive manufacturing for heat transfer applications is most exciting to you. It's a way for the panel to get a feel for what the audience thinks. So I'm going to give a few moments for the audience members to answer, and then I will show the results. And for the panelists, just as a reminder of the poll options, the audience is getting to choose between new properties of multifunctional materials and devices, ultra high performance heat transfer devices and systems, and customization of heat transfer devices and low volume manufacturing. All right, it looks like we've stabilized in the response rate. So we've got a clear majority with ultra high performance heat transfer devices and systems as an aspect that's really interesting. But I think that it shows that there is actually sufficient interest in all three of these areas. And a lot of seeds were planted for the Q&A with your talks. So we're going to go ahead and get into some of the questions. And I'm going to start with a question for Bill King. Did you lower the mass flow rate to enable lower pressure drops, or did you get lower pressure drops at similar mass flow rates while enhancing the heat transfer? I saw that there are a couple of these pressure drop related questions.
So we measured the pressure drop for all of the devices that I presented. I think I only had a couple of slides showing some of the pressure drop measurements and calculations. You know, when you decrease the hydraulic diameter, the pressure goes up for a given flow rate, as you would expect. And so that is, engineering trade-off to make. So there are, of course, applications where you're willing to pay a pressure penalty in order to get higher heat transfer. There are applications, especially mobility applications, where the most important thing is the size and weight of the heat transfer device. And of course, there are other applications where the power required to drive the flow is a very important design constraint. So, the kind of the weight of the pressure drop considerations is different for different applications. For the dual tube heat exchanger, I don't have the flow rate numbers off the top of my head, but what we were doing is we were trying to match the heat transfer performance of a conventional device. And so we were looking at the heat load on the device. And could we improve the device while matching that heat transfer performance? And for that device, we actually had 20 to 25 times improvement in the heat transfer metrics, and also about 5 times improvement in the pressure drop performance at the same time. So it is possible to kind of embrace these new architectures and really get a lot of benefits, and I think change the calculus of how you're thinking about the engineering trade-offs.
I could ask a follow-up to that. What if you had to normalize for that trade-off, normalize that heat transfer improvement by something in order to try to quantify that trade-off? What would it be that you would normalize against?
Well, the figures of merit for that particular project were heat load per volume of the device, and heat load per mass of the device, and pumping power per mass of the device, and heat load per power. So like the traditional heat exchanger metrics. And for that particular demonstration, all of those things improved.
Great, thanks.
Could I add to that?
Yeah, absolutely.
Thank you. Yeah, so I just wanted to add, so we are always, when we have forced flow problems, we add pressure drop constraint, and there's a huge dependence on that. So you can get extremely efficient structures if you allow the pressure drop to go to infinity, and that's of course not practical. But interestingly, for the natural convection problems, we don't need that, because there's sort of a natural trade-off. It wants to promote the convection. And so if the pressure drop is too big, it would be bad. And if it's too low, there's no convection. So it depends on the problems, whether you have to impose a pressure drop constraint or not, or take it into account or not.
Thank you. And we actually do have a question for you, so you won't get to mute that quickly. This one is related to what you discussed in topological optimization. Could you please exemplify in more detail how approaches such as phase field and level set have been used for topology optimization for heat transfer applications?
Yeah, so that's a good question. So I actually had them on this one slide where I showed the many different names that are given to topology optimization. And essentially, in my eyes, almost all these methods are extremely similar. They have a small pros and cons, each of them, but in the big picture, they do the same job. If you talk to different research groups, some have favor one kind of method and others favor other methods. And sometimes they make claims of the others, saying that level set methods have sharper boundaries than other methods, or oppositely. And really, that's often not fully true. So in my eyes, they perform very similarly and are all being used. And for example, right now in these heat exchanger design problems, we have people who work with level set methods and with density approaches, as I use them, and with phase field approaches. So it doesn't really matter. They are all very good methods.
Thank you. We have a question for Bill King from Mark Spector. Are you aware of work applying additive manufacturing to thermofluid components beyond heat exchangers and cold plates, for examples in pumps or valves?
That's a good question. So I am aware of work where folks are using additive for pumps and valves, but using conventional designs. And the motivation for those applications is just economics, that these are in some cases low volume parts, or there's some economic benefit from consolidating parts in a valve assembly, for example. So there's some work like that that's out there in industry. But what's interesting, I think, about Mark's question is, could we exploit, the design freedom of additive to make better valves and better pumps that are more efficient, more compact, that have light weighting? And I think it seems likely that you could. That's actually an exciting idea.
Thank you. So we have a question about this comparison or dual use of additive manufacturing in casting, which Ole, you might want to take it first. What sort of small feature size limitations do we reach if we try to reproduce an additive manufactured heatsink using investment casting?
Yeah, that's a good question. I'm not a casting expert. So my goal is sort of to provide a software where we have different levers. So one lever is overhang constraint, one is minimum feature size, one is pressure drop, and all this stuff. And then when somebody comes and says, I want to do a heat sink using investment casting, then he will select whatever minimum length scale is in this. If you really go to the extreme, then you would also include the actual casting process, maybe in the design process, such that you take this into account. That might be overkill, but if you really want to go to the limit of what's possible, you would do that. But otherwise, it would be good to have sort of what you call it, a manufacturing library saying you use this and this process. Then you have these and these minimum length scale constraints, you have these and these features or restrictions and stuff, and then your design tool takes that into account when it does the design. So that would be the ideal world, and that's when we really mature as topology optimizers, I think.
That's your next project.
Well, we are doing a lot of it already. We have a lot of different constraints, but putting it together in a software that also can be used by standard designers is probably a challenge.
So I just want to follow up on this about the opportunities for casting. So, the structure of kind of the additive manufacturing industry and the way users think about it is that it's the additive equipment that makes the functional part. This is a little bit of a mindset issue. So of course you could use the part for an investment casting, and you could do lots of interesting things. When I've approached additive equipment makers to talk to them about the materials or the manufacturing issues that are related to that particular problem, they've never thought about it, right? Because for them, the printer makes the part. So this is something about the kind of the structure of the industry, and we all think about it, that's preventing interesting things from happening, perhaps.
That's an interesting commentary. I think that particularly the topic of this and hearing from all three of you, we see how interdisciplinary it is, how you can't think discreetly about manufacturing, materials design. This attempt to try to do it really holistically, I think, is the direction that we need to move in. We have a couple of questions that are related, so I'm going to read both of them, but they're both related to fouling. So, and I'm sure a number of the people out there who've worked with heat exchangers have thought about this question. So, so one from Perry Stevens, with these complex internal fin geometries, do we envision issues with propensity for flow channel fouling? And from Nicholas Jankowski, following up to the fouling question, are you aware of any work that has included a fouling potential metric in the topological optimization scheme?
Shall I? Well, I'm not aware, and I didn't even know that there is a fouling potential metric. I would be extremely interested in trying to implement it. I would guess it has something indirectly to do with the pressure drop and the minimum feature size. But if there exists something there where you, based on a flow, can calculate the fouling potential, that would be marvelous to try to implement. But I haven't seen it. So yeah, please challenge me. You could send me this formulation and we could look at it.
Yeah, it's a great question, and you know, an opportunity to extend the research, I think, farther towards end-use applications. Of course, the specifics of the fouling constraint, you know, and the severity of a fouling problem depends upon the fluids that you're using, the specific use case and application. So for some applications, you know, fouling is a very severe, risky issue, and in others, it's much more subdued. So, you know, there's also, I think, some application relevant, you know, constraints that you would want to figure out how to be able to flow, you know, into the design. But, you know, the potential to include the fouling calculations in the optimization is very exciting.
Right, we have a question that it's a set of questions generally posed to the entire panel. What are your thoughts on 3D printed plastic heat exchangers? Do you think there is a wide enough market for them? What direction do you think the research is headed, and where do you think it should head?
Jae-sung, do you want to talk about polymer materials?
Yeah, plastic heat exchanger. Actually, specifically in thermoelectrics, the organic-based thermoelectric materials are basically conjugated polymer. Actually, they are not plastic, I think. But I think that some composite material containing some plastic with some carbon nanotube conducting filler, such as the carbon nanotube, graphene. Recently, those kind of material exhibit some thermoelectric property, even though their property is not that high. So I think that they can be recognized as some plastic thermoelectric materials, I think. Yeah.
I think, I mean, also beyond thermoelectrics, the idea of having an integrated higher thermal conductivity material within a polymer matrix could be used for heat transfer applications where you can print the polymer, but you're getting a higher intrinsic thermal conductivity.
Yeah, there's some very nice work in the literature on polymer additive heat exchangers. They seem to be best for applications where you have low flow rates, where, you know, the overall where the heat transfer is dominated by convection resistance rather than the wall resistance that's high because of the low thermal conductivity of the polymer. But this idea that we could have composite materials where we, you know, included high thermal conductivity fiber or powders, or found new ways to merge polymers and metals together. There's a lot of interesting opportunities there.
Ale, I wonder, for the LED application you talked about, did you look at printing the structures from a polymer, using a polymer instead of a metal?
Well, I think that would not, they are so depending on the conduction there that they would simply not work, and definitely they would look very differently. So I'm not sure. Then I think it would just want to make the biggest sort of flat surface to do the convection there, and probably it couldn't even do the natural convection. There wouldn't be not enough power in it. So I'm not sure it would work there. I think you need it for the forced convection problems. That's where it works, but not for natural convection, is my intuition at least.
All right. We have a question from Xiaobing Liu. With current 3D printing technologies and available materials, can a 3D printed heat exchanger be waterproof? In other words, have no leakage?
Yes, absolutely, they can. I showed several. The powder-based processes for metal additive, I'll say a little more. So for the powder-based processes, have really gotten a lot better over the last 5 years or so. So maybe in earlier days, the materials coming out of a commercial printer were more porous, and you had to, be concerned about maybe leakage issues. But you can really, with DMLS and other metal additive processes, you can make a fully dense part now that's watertight even with thin walls.
And how did you tackle surface roughness and all of the metal printing that you did? So this is a big difference, I think, when you're doing additive. Did you do any post-processing?
We did not do post-processing. We lived with the roughness that we got. The roughness was small. The surface roughness is an issue. And in fact, there's some work in the literature that shows that the roughness of metal additive parts affects the flows in unusual ways. So there's some strange issues with kind of slippery boundary conditions with those metal additive rough surfaces, because they have just a little bit of porosity as well. So that seems to affect the flow physics, especially at higher flow rates. So that's opportunity for more R&D for folks to really kind of sort out what's going on. But Sonia, as you point out, of course, you can do post-processing that would smooth the surface. And I mean, there's a host of metal additive technologies out there that would allow you to get the surface that you want with the right treatments.
Great. I did see that the panelists were answering some of the questions in the Q&A, but there was one question in particular that, in case folks can't see the Q&A, that I was hoping people would answer, broadly, so that people listening could hear. So there was a question regarding cost, and I think that might be on the mind of some of the people who are watching this. So will additive manufacturing yield substantial cost reductions thanks to the major improvements in power density and material use, or do the economies of scale of traditional mass manufacturing have an edge? So I think that there's some discussion here around cost, volume manufacturing. How do you make the decision with those aspects in mind? So I would certainly like to hear from the panelists on this topic.
I'll go first, and then the others, I think, have interesting things to say as well. I personally think the really interesting opportunities from the university side are the applications where additive provides a benefit that you can't get with traditional manufacturing, whether that's new geometries or new materials or new heat transfer capabilities, perhaps. And so for those cases, there's no cost comparison because you can't get anything from traditional. But when we think about things that are closer to an application, already today there are cost benefits. So additive has a cost advantage over traditional manufacturing for some parts, some geometries, and certainly low volume and customization applications. There's already a big economic advantage for additive over traditional manufacturing. And for larger volumes, then additive does not have an advantage. The additive cost curve still continues to evolve rapidly. So this is not a static equation, that it's changed even over the last 2 years or so, and I think will continue to change. There's actually a host of new metal additive technologies that are coming out that are like similar to metal injection molding. And these may have offer some type of step change improvement. So it's still very early, but there's really quite a lot happening in the industry that I think the situation will continue to evolve.
I think I can't add much to what Bill said there. So surely we cannot compete against car cooling systems and stuff that is mass manufactured. We have an application in cooling for CPUs, And there people turn out to be willing to pay a lot of money. I think there's people of gaming industry where they spend a lot of money on fancy water-cooled systems and stuff. And if you there can make it more efficient, people are willing to pay for it. But in the big picture, we have to pick the right applications and not compete where there exist fantastic products already.
I have a follow-up question to that. When you do the optimization, do you have an optimization approach that incorporates cost into it? So for example, where you would end up with a topology that might not be completely optimized for the heat transfer performance, but has a balance between cost and heat transfer?
Yeah, so I guess it's like the manufacturing constraints that we can also put the cost of support. So a very expensive operation is when you have manufactured your device, then you have manually to remove support structure. And so we can put in the cost for that. And then you can have this trade-off curve, cost and performance, and you can select the point you want there. So definitely this is something we want. But of course, it requires that you know what things cost. And if you have this geometry, what does that cost? So if we have something that is quantified and well defined, well, then we can put it into the optimization. And then I'm back to the sort of the levers that ideally we would have levers for everything. And then the designer selects the value that holds for his manufacturing process or the labor cost in his country or whatever. So that would all be in the optimization.
Jason, what are your thoughts related to the cost and the?
Yeah. Just in thermoelectric model, as I shown before, basically the thermoelectric model in total cost, the material cost is as high as 40%. And as I mentioned before, in traditional manufacturing process, we lose about 60% of materials during the dicing process and the ingot synthesis. So if we apply additive manufacturing process for producing a thermoelectric motor, I think we can save lots of money in the material cost and processing cost. Also, we can simplify the processing for manufacturing, because basically the thermoelectric motor manufacturing is a multi-step processes. So I think we can simplify at least 3 steps, the dicing process and ingot synthesis by the 3D printing process. So it's gonna be very beneficial for reduction cost.
Thank you. We have a question about air heat recovery. Could an air-to-air heat recovery ventilator be made with thermoelectrics embedded in it that was able to power its own fans? Perpetual ventilation.
I think I always get nervous when people talk about perpetual anything. But I would guess that the loss, so essentially the thermoelectric generators are not very efficient. They're excellent for recovering waste heat, but they have not a very high efficiency. So I think the energy would get lost there. But much more interesting is the convection problems, the natural convection problems that I discussed. So you have some heat that drives the ventilation, and in that way you make the heat transfer. So that could sort of be not a perpetual ventilation, but a self-driven ventilation. And that was important for these LED lamps, because they are used for concert halls and other places where you cannot have a motor or ventilator running. You want something that's silent. But maybe, Jason, what do you think about the efficiency of thermoelectric generators?
I think that such a fan, the ventilation fan system, air heat recovery system, for getting higher thermoelectric efficiency, the most important thing is the higher delta T across the thermoelectric material. If we can making higher delta T by this system, definitely we can get higher efficiency. Well, I don't know if we can realize such a air-to-air heat recovery ventilation system by additive manufacturing.
I wonder if I could maybe extrapolate from the question about net power. One of the things that people analyze with thermoelectrics is essentially net power, the power generated, but minus the power required to operate whatever it is you're using, whether it's a fan or something else, to enable forced cooling on the cold side. Have you investigated that? Because you are showing higher efficiency with the 3D printed thermoelectrics. Have you looked at how the net power changes?
Sorry, I didn't investigate such an approach. Yeah, let me explore in the future. Sorry.
Yeah, it's a harder one because you have to think about what's driving the cooling on the cold side.
Yeah.
And I think we have one final question. Additive manufacturing has the potential for highly localized and variable process and material property control absent from traditional manufacturing. Do you see any particular heat transfer use cases to leverage this control or variability? And I think that's applied to the entire panel.
Well, I could refer back to our thermoelectric generator study. That was our hope, and we had seen in the literature where people claim that if you match two materials in some intricate manner, then you could get higher efficiencies than anything. But it turned out that depended a lot on the model and on the boundary conditions and stuff like that. And so we ended up not seeing anything special. This is in contrast to some dynamic problems we have been looking at earlier, where you can sort of damp or attenuate propagating waves if you have very heavy masses in a soft polymer and stuff, and make band gap structures. And so we were sort of hoping a little bit to see effects like that. I haven't seen that much in fluids yet for that. Maybe when combining with acoustics, then you would be able to design very intricate structures that absorb or reflect waves in certain ways. Maybe also if you go to the nanoscale and you start looking at phonon transport, you can do interesting stuff by controlling heat propagation and stuff like that. But that's another business to go down to that length scale, I think.
So this is an interesting question. I'm not aware of work that people are doing in this direction, but it for sure seems like there's an opportunity. One topic that's been on my mind is how to exploit the ability to control local porosity in a material. So could I have porosity gradients that were tailored with sub-millimeter scale resolution throughout an entire device? And are there energy systems or thermochemical systems that might be enabled that today use porous materials, but if you could tailor the porosity in 3 dimensions, what new things could you do? That's very exciting.
I agree. I'd love to follow up with you on that, because I've been thinking the same thing. So that was wonderful. Thank you all for your insights and for sharing the work that you've been doing. We're going to end by again polling the audience with the first question that we asked you to see if your minds have changed now that you have heard from this panel. So again, if you wouldn't mind answering the question, in how many years will additively manufactured heat exchangers and thermal management devices penetrate and have high impact in an application? And just for the panelists, the options are 1 to 5 years, 5 to 10 years, and 10 or more years, as a reminder. And it looks like you have influenced the thinking of the audience, which is really exciting. And so now we have belief that the majority is saying 1 to 5 years. So I think that's representative of how you really influence the thinking of the audience with showing the cutting edge work that you're doing, that they now think that it's coming sooner. So that's really exciting. I would like to end, so I want to thank all the panelists. I thought this was fascinating, but I'm also a nerd when it comes to additive manufacturing and heat transfer. So hopefully we have gained some more enthusiasts in this field. I am going to end the session by mentioning that the next webinar is in 2 weeks at the same time. And the topic for that is aligning policy to decarbonize thermal energy systems in industry. So I'm also looking forward to that one. It looks exciting. And then lastly, if the participants wouldn't mind, as well as the panelists perhaps, if you'd please type in your suggestions for future events, speakers, topics, or formats. Sorry about that. You're encouraged to sign up on the email list, and past event videos and Q&A will be on the website, so answers to the Q&A. So thank you all for attending. I thought this was a wonderful discussion. I hope it seeded some enthusiasm and curiosity about this topic. Thanks, everyone.